Our first speaker for the morning is Vera Serganova, who will tell us about similarities between representation theories of finite groups and positive characteristics and leaf superalgebra.
Okay, thank you very much for inviting me. I enjoy this conference, and I would like to talk about similarities between two representation theory. I would like to start maybe to mentioning that it is kind of a long project already for a few years, and I would like to write down my collaborators here. So I have 3 collaborators on different parts. Ina Eisenbart, Alex Herman, and Arkady Weintraub. And so let me start with talking about certain tensor category, which is Frobenius symmetric monoidal rigid category. In addition, it is k-linear. And I wouldn't write all the axioms because mostly we're going to talk about 2 examples, but let us assume that K is algebraically closed, although probably it's not so terribly important. So the things which we should understand about these categories, the first thing is that such a category has a notion of trace and the notion of dimension. So for any endomorphism of an object, we can define the trace with its values in K, and we can define dimension of X as a trace of the identity map. Okay, and the fact that it is Frobenius, that means that it has enough projectives and injectives, and that's basically it, because every projective is injective by duality. Okay, so projectives. So there are 2 examples we are going to talk about. So example 1, if we take a finite group, and we do have say G, and K is of positive characteristic P, actually could be 0 characteristic, but then it's not so interesting. And we just consider finite dimensional representations of G, which I'm going to denote by G, and this is such a category. Just let me mention that dimension of X, this categorical dimension, is a usual dimension or image of the usual dimension in a FP, if I can say this way. Okay, so this is an element of FP. Now my second example is an algebraic supergroup. I'm going to talk a little bit more about the definition later on, but this is an algebraic supergroup G, and every algebraic supergroup has an underlying usual group G0, and I assume that G0 is reductive, and my field, let us say it's just C, because the things I'm going to prove later on, I need that it is actually C. And then the trace, categorical trace of a morphism. So we work now in the category of vector spaces with Z2 grading. So every vector space. So work on this vector. One, and the trace of phi, it is what's usually called super trace of phi, is the difference trace V0 phi trace 0 phi minus trace on V1 of phi. Okay, so all morphisms, we are working with abelian categories. All the categories I'm talking about are abelian so far. And so this is the trace and the dimension of V is going to be difference of dimensions of V0 and Août. V0 and V1, and it takes values in Z. So for us, this is important because especially we make a huge difference between objects which have 0 dimension, categorical dimension, and non-zero dimension, right? So next, I would like to talk about two important constructions. Construction one essentially important for Frobenius categories. And so if we start with C, such a category, one can consider the stable category. By the ideal, and Joshua very conveniently for me introduced it last time. So it's just the ideal of all quotient bimorphism through which can be factored through morphism to the projective. So, and this is not a Pelian category anymore, but it is triangulated category. And it is still tensor category, and in many things, for example, in support theory, people prefer to consider such a category. And this is the first one, so this is stable category. And then there is a second construction, and the second one is semi-simplification. So what we have in this case, we consider category C1, which is again a quotient category, but the ideal of all negligible morphisms. So again, objects are the same, but the quotient morphisms, but the ideal of negligible morphisms. So morphism and from X to Y is negligible if for any psi, morphism psi from Y to X, Y psi has a 0 trace. So the category is the semi-simple tensor category. And maybe I should say one more thing, that simple objects of R are isomorphism classes, okay, are indecomposable objects of decomposable objects of C of non-zero dimension.
Should that be for all psi instead of there exists psi?
Or for all psi. Oh, yes, yes, sorry. For all psi, of course. I'm very sorry. Yeah. Okay.
How does it compare to getting rid of the morphisms which pass through an object of dimension 0?
Yeah, I think, no, I'm not sure. I'm not sure. Sorry. I don't think it's enough. I mean, okay. So now I'm using this port, right? Okay, so now what's my next thing? Now I would like to see what I would look at this example and see what I can say, okay, in both of these things. So first, let us talk about semi-simplification, because so now if G is a finite group, and I did not by big P, just a P Sylow subgroup. And I will take subgroup K, which is a normalizer P, or actually any bigger subgroup will work as well. Yes, I might say they have the subgroup like this. And the point is, so this is a very, so basically I'm going to talk about two statements and one, you know, right. If I take representation of G, then I semi-simplified. So bar means a semi-simplification, then this category is equivalent to the category of representations of K. Semi-simplification of the category of K. So this is a particular case of a little bit more interesting result, which I don't have time to talk about, which is called green correspondence in the theory of groups. And in particular, that means if I start with a decomposable M and I restrict to K, then I can write as a sum of decomposables with respect to K. And maximum one indecomposable have non-zero dimensions. So remember, dimension 0 means actually that the usual dimension is divisible by P. Okay, so this is a functor, and you can take an induction. So it's not a very easy, difficult theorem, and it's basically this theorem follows from this green correspondence in this particular case. So there is a bijection between the decomposable representation of non-zero dimension over K and over J. Okay, so this is the first theorem. Now let me go to the second one. Suppose that the Sylow subgroup P is just a cyclic subgroup of order P. The simplest possible situation. When we actually have equivalence of triangulated categories, which are stable categories for G and K. And basically again, the restriction factor and induction factor gives you this equivalence. And I would like just to make one remark, which makes the difference between these two examples. So it actually relates to the second theorem. When I do the semi-simplification, if I work over characteristic 0 and say algebraic supergroups, and I take a semi-simplification, I'm going to get again category of representation over some group, which is maybe pro group, but it's still something which has a fiber functor. But in characteristic P, for example, if I start with Z mod P or with a cyclic group of order P, I'm going to get Verlinde category, which is not the one which has fiber functor. So it's not Tanaki, and it's not representation of any pro group. So simplification is not, doesn't have fiber functor. So for the rest of the time, of course, I'm going to talk more about supergroups. But if you have any questions right now, good time to ask.
If you use any finite group, does the semi-simplification have a functor to the Verlinde category?
Yes, Z mod P. Yes, Verlinde.
Yes, but if I take any group and I take the semi-simplification of G,
yes.
Is there a faithful functor to the Verlinde category?
This is not exactly like this, but there is work of Ostrich. I'm not sure that this is exactly a statement like this, but there is some similar statement which I'm not sure. So maybe I will talk now a little bit about supergroups. So now we work over here. And we're talking about the group object over vector superspaces. So you can think about supergroup. One of the possible ways is to think about this ring, which is a Hopf superalgebra. And it is in particular supercommutative ring. Okay, so what is important here, right? If I take this Hopf algebra, I take the ideal generated by all odd elements, I get a usual Hopf algebra. Yes. 0. So this is also what's called underlying group. And it's an easy exercise, actually, that the category of rep G is Frobenius if and only if G0 is reductive. So we call such group with reductive zero part, we call them quasi-reductive. So the point is that if you look at the classification of simple groups, simple supergroups, actually, let us start with Lie superalgebra. So, of course, there is a Lie superalgebra associated to any supergroup. And from classification of class and representation theory, we will see that there is very little supply of supergroups, which are not usual groups, which have semi-simple category of representations. Okay, actually, it's only one series, OSP1 to N, which has semi-simple category. All others are not semi-simple, but they are Frobenius. And one of the possible ways to study is actually try to make the analogy. And I don't know why we didn't do it earlier, probably because I didn't know well enough the theory of modular representations of finite groups. Okay, but I think it's actually very interesting how much you can generalize. And I need an example, so let me give you an example now. So my example will be, of course, Gilliman.
I should mention that we actually thought about this a long time ago, detecting subalgebras.
Yeah, I will relate. I will talk about it. Detecting subalgebras, of course. Yeah.
We were actually motivated by finite groups.
You are, but not me.
We were looking at these categories. We were motivated by finite.
Yeah. So actually, yes, I should say that work of Dan and his collaborators, Kuyava, Bowie, Grancharov, and there is some parallel theory using support theory. I'm talking about some quite a little bit different approach, which uses more geometry. And you will see how it is related. Okay. Yeah, maybe I should do examples too. So I start with some superspace finite dimension vehicles. I call it C, M, N. This is even, this is odd. And then I can just take an automorphisms of V as a functor. This is GLV. And G0 in this case would be GL0 plus GL. We won, so I usually call GLMN. And so what else I should say? Maybe I should say that the Lie algebra, GLMN, is just all these matrices, block matrices, PD here. And the even part is diagonal matrices and off diagonal matrices. Okay, for and fall. Odd part, super trace equals 0 means that we have a cell element. And I just would like to write down what is the group as element because I need a formula for Berezinian later on. So Berezinian of the matrix like this. Okay, so it's defined on invertible matrices, and if I put it equals to 1, I get the super group as element. So Berezinian is an important thing because you can talk about Berezinian shifts on supermanifolds, and that's what I need actually to define the integration. I need Berezinian shifts later on. Okay, so now and so now what I'm going to do, I actually would like to formulate and sum by theorem 1 and theorem 2 in this setting. And for this, of course, I have to understand what is a Sylow subgroup. And that's what I'm going to talk for quite a while. So basically, what I want to do, I don't want to get out of class of quasi-reductive groups. So we work in quasi-reductive supergroups. Okay? And so one of the differences with category of finite dimensional, of finite groups is that the induction of some, say, finite dimensional representation of V is not in the representation, is not in real G, but only in its inductive closure, because this is an infinite. moreover, what is this? It's just sections of a vector bundle on a super variety, homogeneous super variety, G mod K. So there is a work of Mazoka, which actually explains that this is well-defined super variety for us is important. So if I call this super variety big X, okay, that this is an affine super variety. And so the induction factor is exact, although it doesn't go to representations. It goes to all representations. It's of course infinite dimensional. So we actually have the geometry here, and that's what I'm going to talk about.
Is there any assumption on K?
Oh yes, K must be, yeah, both, yes. So G and K are quasi-reductive. That's the whole point. I'm not going to consider, I'm not. So basically, if I take an underlying variety, this is just G0 mod K0. And this is a fine. Yeah, just exactly because of this is variety here. And so we are going to define K, which is always quasi-reductive. I will not going G. It's called splitting. If I induce from the trivial representation, and in this induced representation, C splits C, which is naturally C is their constant function, splits as a direct summand. Okay. But what does it really mean, and why such a group is a good group? So basically, for example, that means that if I have an exact sequence, short exact sequence of G modules, and it splits over K, then it splits over G. That means that if I take a restriction factor, then the X group defines a direction on the X group. So of course, in my first example of finite group, splitting group is very easy to describe, because if I have a splitting over K, I can take average over homogeneous space G mod K. I can take an average. And if its average doesn't give me 0, then I do have a splitting over G. And this simple argument tells me that K is splitting. So for finite groups, even only if P doesn't divide the index, or in other words, K contains a Sylow subgroup. In that way, I can say that the Sylow subgroup is a minimal splitting subgroup. So, and that can be taken as a definition of a Sylow subgroup or a supergroup. So one important thing about splitting subgroup is that the restriction factor maps negligible morphism to negligible morphism, and therefore it induces a factor of semi-simplifications on semi-simplifications. Okay. Well, now I would like to give you, so what is the point? The time doesn't show anymore, so I still have some time, right?
Yeah.
Okay, good. But you see, we even don't know that such a notion as a minimal split. We didn't know that this notion of a minimal splitting subgroup makes sense because you have to check something to show that it has a minimal splitting subgroup. Now we can. So maybe just we have we constructed minimal splitting subgroups for all simple quasi-reductive groups. And they are exactly like detecting subgroups in your case, but I don't know if you have one for P and we have.
Yeah, we did.
Yeah, so anyway, we do have this, and now we have conjecture, which we checked again on simple subgroup, but we have Sylow theory, but to written subgroups are conjugate. And I really believe that we can prove it. It just we need a little bit more time. And the proof which we have now is not very conceptual proof. It doesn't work like a proof of Sylow theory. So now I would like to give you a couple, explain a little bit the propositions. So a couple of things which we can prove. So the first one, so if we have a splitting subgroup, when we have a certain geometric condition, namely for any, so I have to introduce something else. I should take the Lie algebra G, take this odd part, and consider all elements X in G1, such that commutator of X of itself is not zero, as in general, zero is a particular case, it's semi-simple in G0. And so the condition is that every adjoint orbit under the group G0 and G0 orbit of X, which is homological, intersects K. Okay, and the idea of proving this, if this is equivalent to same, maybe I should. I look at this homogeneous space, I find super variety G mod K, X, and I have this little X, and it produces a vector field. So this is a vector space, wood vector field on X, and this condition is just equivalent. So if condition is not true for some X, when that means that Lx doesn't have a fixed points. Lx doesn't have fixed points. Vector field feature doesn't have fixed points. So then there is this factor. Basically, it's cohomology. What I do, I take C of X, take invariance with respect to X. And then, so now on this X squared is 0, I take homology. So I take homology of here, X over image X on this. And this is 0. And since it's a 0, C couldn't split. Okay, that's the argument of result. But so in the situation of finite groups, we basically look at number of elements and number of conjugacy. No, sorry, number of cosets G mod K. And I would like to do something like this in supercase, and of course I have to introduce integral. So there is a certain, there is an integration theory, which is called Bayesian integral for supermanifolds. So Bayesian sheaf is exactly the sheaf which is changed given by the Bayesian which I wrote before. It is something which you can take integration of. Okay, so Bayesian X is the line bundle on X, and X in this case is supermanifold. And what I can do is since X is affine in my situation, I can have an invariant splitting. I not only have this, but I have a projection like this. Okay. And if I have a section of Berezinian here, so one important thing that the fibers of this are just affine. These are affine superspaces. And so I got to the volume forms. Okay, and this splitting is invariant with respect to G0. So if I have, so suppose that actually is a, so both of them in our case, when X is the homogeneous space, both of them are G shifts actually, right? And so suppose the shift Berezinian X is isomorphic to all of X, which means actually that I have G invariant volume form here. So that exists. X, let us call it omega. Okay. And what I can do
You use volume form X cubed?
on X. Yes, on X. So this is a section of Berezinian shift, which is invariant. Okay. So what I can do, I can take, suppose I have any function f, c of x. So what I can do, I can take Berezinian integral I of f, which is going to be f integral, and I have to explain what is this integral. And here what I'm going to do, I'm going to take f omega, which is another form. I can take push forward. Okay, push forward is exact in this case. And what I'm going to do, I'm now going to integrate over x0, but not really over x0. I'm going to pick up a compact cycle sitting inside it. The point is, in this particular case, I know that I have a compact real form here. So G0 over K0. Inside it, I can take maximal compact C and quotient by maximal compact. So this is something like unitary trick, actually. And I can integrate this form over this cycle, and I get some complex number, right? So I'm going to get the map to C. And the point is, and that was actually noticed first by physicists, I think. So this technique is called CS integration, complex manifolds, and actually was first discovered by Witten. But the point is that in our case, it works very, very good. And so, if I am in such situation, I do have an invariant map from C of X to C. This is an invariant map which I call I. And if I want to use this map on splitting, that means, so I1, which is just, I call the volume of this X, super volume. This must be non-zero. And that gives me the splitting. So in the way on this, there's a lot of technical work, but in the way it's a very simple argument. There is some, but how do I know that this is all possible? So this is the next theorem. So first of all, I need a condition that such invariant volume form exists. And so this is very recent theorem that G is splitting if and only if. First of all, G mod K, it meets invariant volume form. And second, the integral of this volume form over G mod K is not zero. This is if and only if. And that, for example, means from this we can easily deduce now. And basically, this is the same thing, right, as an index. This is the right way to define the index.
There are constant, suppose there is. What is that? The constraint is assumption.
Because I need the SG shifts. So for this, I need an invariant volume form. If I have an invariant section, that exactly gives me, this is the same way as to say that this is an isomorphism. And we need to prove it, we need this. And this is actually very recent. So just Alex Sherman visited me 2 weeks ago and we sort of figured out, but I think it's quite nice. It's very simple actually in the end of the day. Okay, so now the question is, of course, a couple, maybe I should now say about theorem 1 and theorem 2. And then, of course, there is a big thing, how to construct this splitting subgroup. So basically how to check when this volume is not 0. And I just say on words. It's actually the only technique I could find was to use what is called Schwarz-Zboronsky formula. This is super generalization of Westermatt-Hoffmann formula, which most of you know. So if I have a suitable odd vector field, say with isolated points, and I would like to integrate the volume form, which is invariant with respect to this, I can do this as a sum of local contributions at these points. That's exactly how my X, which I was explaining before, this odd element X induces this vector field. And if X is generic enough, I can find, so I can choose it in such a way that it has discrete set of fixed points, and I can just compute contributions. So it's the work with Dmitry Weintraub, but I don't have time to explain in more detail, but the main idea is this, doing something like the Westermatt-Hoffmann formula in supersettings. You have to generalize it to CS setting, because original formula 1999 of Schwarz and Zaboronsky, it was for real supermanifolds, but you can do it in this setting. So, but now let me talk about theorem 1 and theorem 2. So theorem 1, if you remember, this is green correspondence. And there is some trouble here because we don't have this thing. So suppose P be splitting, minimal splitting subgroup, and K be the normalizer. Okay, then I do have a factor, restriction factor between semi-simplification, rep J to rep K. And this factor is fully faithful, but in general, it's not essentially surjective. But not essentially subjective, so we don't have equivalence in general. It is kind of an interesting problem to understand the image, okay? But that actually means that a secret supergroup, reductive supergroup sitting here, this supergroup is a quotient of this supergroup. And what we hope is we have some discrete kernel or something like this. But the second one, so before formulating the second one, maybe I should explain.
I think the formula is at least it could be online. In this case. That's what I was saying.
Yes, this is true.
Yeah, so the kernel model is the formula.
Okay, so now the second thing is, so maybe I should at this moment to tell you, okay, I should stop. But you give me 3 minutes, right? Okay. So my example of GLMN, let us assume that M is less than N, then what is K in this case? So we take a L11 to the power M sitting inside, and then semi-direct product with a symmetric group, and then product with GL and minus L. This is my K. So what I would say, what does it mean that a Sylow subgroup is a cyclically minimal one? Yeah, suppose P is just the L11. So there are many other groups. So all exceptional groups are of the same sort. Then we have just the same stable category. The stable category of G. And so this is my, oh, I should put here gel. And my P is just SL11. And this is my K. So then stable categories. Then of course it involves the semi-simplifications. Okay, and I stop here. Thank you.
Behind the stage already one question, and the rest can be in the coffee break. Any questions for that?
I mean, can you comment on what happens if n does equal n? Something drastically different happen.
Oh no, actually not so drastically. I mean, so the most important characteristic here, what is called defect. Okay, and so in a way, there is an equivalence of blocks of GLMN and GLNN. Okay, so there is an equivalence of blocks. You have more blocks. Blocks are basically enumerated by this part. So from homological point of view, there is not so much difference. Okay.
Two announcements before the coffee break. So the next talk is at 10:35. So we're going to have a coffee break and a poster session in the same place. The posters will be displayed until the rest of the day. So if you want to continue talking about that, you're welcome to. And the last thing on the schedule for today's research discussion